Act 2, Scene 4, The Palace, a street. Enter Antipholus of Syracuse and attendants.
A common trouble prisoner, and to lay stay in her hand, and that thou art the cause of my poor lord, and therefore by to thee, and then lo are thy son.
I hope the poor prince of Caesar shall be so.
And sir, I have another to you better. How marry me there, when I may bring the body of the world, and I was buried as the state and more, then they are proved. So these lines were actually generated by a recurrent neural network that was trained on our computers. In this video, we want to present our results when we try to understand how recurrent neural networks work and how they learn on real text. Traditional neural networks are not very good at processing sequences of information, so they perform very bad on real text and text generation. We need a way to keep track of information that was processed in the past to make better predictions in the future. And this is exactly what recurrent neural networks do. So how do they work? The general idea is that the hidden layer of our recurrent neural network does not only take information from the input, but also from its own state one time step back in the past. So in this example, in the first time step, we feed an input into our network, which is, the input is green in this illustration. And the hidden state at time 0 depends on the green input. At the next time step, time 1, the hidden state of the network also depends on the previous hidden state. So that's why it's green and red. And so on, and in time step 3, we see that the hidden layer state depends on all previous hidden states that the network had seen before. This is how recurrent neural networks afford to memorize information from the past and to use it to predict future sequences. Let's go more into the details. Here we see what the model does at different time steps. We call this representation of a recurrent neural network an unrolled version. At time step 1, we feed in the letter H, which serves as our input here. And the input is usually represented as a one-hot vector that is the size of our alphabet and is all zeros except for a 1 in the place of our input letter. The input is then mapped onto the hidden space of the network, the hidden layer, which is done by multiplicating the input by the weight matrix WXH. At the next time step, we feed in a different input, and this time the hidden state of the network does not only depend on the input E at the next time step, but also on the previous hidden state of the network. In the end, we use the weight matrix WYH to map the hidden state of the network onto the output space, which is where we get the model's predictions. So in total, we have 3 weight matrices in this network, which are WXH, WHH, and WHY. How do recurrent neural networks learn text? The general idea is that we use a text sequence as input and use exactly the same sequence as output, but shift it by 1. In this way, the model learns to predict the next letter after seeing any given letter. How does it actually learn that information? The model uses a loss function that tells us how far off our predictions were. Usually we use cross-entropy loss. It then calculates the gradients of the loss function with respect to the model's parameters, which are the values in our 3 weight matrices. In other words, when it is learning, the model updates the way it maps the input space onto the hidden space, and the way it maps its hidden space onto the hidden space one time step further, and also the way it maps the hidden space onto the output space. In order to accurately update these weights, we have to unroll network as shown in this illustration and backpropagate the gradient through time, which is why the algorithm is called backpropagation through time. So we found code on the internet that implements this basic concept of a recurrent neural network only using Python and the NumPy library. The code is by Andrej Karpathy, and after running the recurrent neural network for a couple of minutes on our laptops, we got these results. So at first sight, it doesn't really look very good, but we see that the model has learned something about the text. For example, the length of words and also punctuation seems to be quite good. After running it for a few hours, it produces a lot of words that are valid words in English language. So the text doesn't make sense, but it still looks pretty good.
So recall that we said that RNNs use backpropagation through time, and this is basically quite similar to standard backpropagation, but there's a slight twist. So for clarity on these slides, we let y hat be in the equations be the output at a particular time step, and S3 is simply the hidden state at time step 3. So calculating the gradient of loss, or the error, at time step 3 with respect to W is a chain rule that involves the partial derivative of S3 with respect to W, which you can see right over here. Remember also that W is simply just a learned matrix for integrating the hidden state at any time step with the input at that step onto the next hidden state, which is the recursive step. So looking at the formula for calculating the hidden state at time step 3, which is right here, we can see that S3 actually has dependency on S2, and which itself then has dependency on W and S1, and so on. So the problem is that we cannot just treat the hidden state at time step 2, S2, as constant in the chain rule, which is why we must sum the contributions of each time step forward towards the final gradient. So because W is used in every single time step up to the output, we need to backpropagate the gradients from t equals 3 all the way to t equals 0. It's also important to note that the derivative of the hidden state at time step 3 with respect to the hidden state at time step k, so it'd be this term right here, is also a chain rule in and of itself, because we're going to have to compute ds3, ds2 times ds2, ds1, and so on. So this leads to a sort of a problem which is called the vanishing gradient problem, which we'll introduce really briefly right now. So as you can see, we'll have to basically carry out a large multiplications of all the derivatives of the hidden states at different time steps. And taking the derivative of a hyperbolic tangent function yields a function that approaches 0 at both ends, as seen in this graph, in the green line. So as we move further and further back through the hidden layers, in other words, as we take more and more time step backwards, the gradient of the error function with respect to the very early layers' weights will become extremely small. This is simply because our hyperbolic tangent function, by definition, will squash any input into a very small output range. So large regions of input space are mapped into a very small range. So this means that even a very large change in the input will end up producing very small changes in the output, therefore a very small gradient which vanishes. And this is further emphasized when we stack multiple nonlinear layers. And eventually the hidden states of the earliest time steps don't even end up contributing to what the network is learning. Therefore, we cannot learn any long-term dependencies, which is a really big problem when we're trying to learn text and sequences of letters and characters. So there are a few solutions to this problem. One is just to use a more appropriate activation function, such as the rectified linear unit. So taking the derivative of this function yields a constant of either 0 or 1, and this makes it one of the most popular activation functions for deep neural networks these days. Another solution is to integrate what is known as long short-term memory cells, or LSTMs, or gated recurrent units, GRUs, into the recurrent neural networks architecture. This solution allows for more learning to be carried over with each recursive step. That is, every time we pass over the hidden state to the next time step. In particular, implementing these gates and these cells allows for greater selectivity in terms of what we wish to retain. So we'll start by introducing GRUs a little bit. So GRUs have two gates, and the update gate Z defines how much of the previous memory to keep, while the reset gate R determines how to combine the new input with the previous memory, or the previous hidden state. Meanwhile, the variable H is basically a candidate hidden state, which is based on the reset gate R, but we use this to calculate the actual new hidden state ST, which combines the results from both the Z and R gates. And so this ST is the one that will be passed in a recursive step for the next time step.
So this slide we'll talk about the long short-term memory recurrent unit. Compared to vanilla RNNs, which only combines the previous hidden state as part of the input for the current recursion activation function, the LSTM has a gating system that allows control of how learned dependencies are updated. And explicitly, it has 3 gates along with a cell state C that keeps track of the learned stuff. So the core thing in LSTM is a cell state. And for each recursion, there are 3 gates: the forget gate here, the input gate here, and the output gate here. So first, we have the concatenated input of the previous hidden state and the current input that goes through the forget gate and filters the previous cell state C, which is CT-1. Then the same concatenated input goes through the input gate and the activation function, and then combines part of itself with a filtered previous self state. And finally, this new candidate self state will go through the output gate and will produce the output y here. And that is how the LSTM does a recursive step. And now we have the short comparison with LSTM and GRU. So the LSTM unit computes a new memory content without any separate control of the amount of information flowing from the previous time step. Rather, it does control the amount of the new memory content being added to the memory cell, though, independently from the forget gate. And on the other hand, the GRU controls the information flow from the previous activation when computing the new candidate activation through the reset gate, but does not independently control the amount of the candidate activation being added. And that control is tied via the update gate. And as also empirically evaluating a paper, it is difficult to conclude which types of gating units will perform better in general. The learning rate of both LSTM and GRU on the long run on the same dataset are roughly the same. And though they are almost equivalent, for us, GRU has 2 gates instead of 3 for each recurrent unit. So that will be computationally cheaper, so we'll stay with GRUs for experiments.
So we decided to study and implement a working example of GRUs at work in a recursive neural network for character-based language modeling and text generation. So some of this code shows some of the parameters that were used. So we can see that the number of times each GRU cell was enrolled was about 30. The size, we can see the size of the training batch, the internal size of each GRU cell, which was 512. And this basically just stands for the dimensionality of the hidden space of each GRU cell. We can see that the number of GRU layers was 3, and we can see some learning and dropout parameters. So the model uses GRU cells, which have, by default, hyperbolic tangent activation functions. So the model also uses a cross-entropy loss function, which seems pretty common in recurrent neural networks these days. Finally, the model uses a softmax readout layer that takes in a k-dimensional vector of arbitrary real values and outputs a k-dimensional vector of values between only 0 and 1, which all add up to 1. And this is done just so that we can basically predict which is going to be the most probable next character in the sequence, which will be the number of the greatest magnitude in this outputted k-dimensional vector.
In order to get a feeling for how much GRUs improve the performance of our model, we compared the results of a TensorFlow implementation of a recurrent neural network using GRUs on the same Shakespeare text with our initial plain Python and NumPy implementation. So on the right, the model has mostly words that are valid English words. It correctly capitalizes the names of the persons on the stage, and it even has stage directions in brackets.
So we decided to experiment a little further with the TensorFlow model, which proved to be the best in terms of performance. So we manipulated the number of GRU cells present in the network while keeping any other parameters constant. So although the network was trained only for one full presentation of the full Shakespeare dataset, so all of his works, we still found some pretty interesting differences as a result of this manipulation. So the graphs basically show the accuracy and loss as a function of the number of iterations for both the training and validation data, so top and bottom graphs. As can be seen, having 3 layers rather than just the one resulted in the network being able to capture some higher level interactions and dependencies. However, doubling this number up to 6 layers did not really yield any improvement, which could perhaps due to some overfitting or slower initial learning. Maybe this could also be a result of how the weights were initialized in the network with more GRU layers. However, we might actually expect a slight advantage of 6 layers over 3 if we were able to train a network for much longer, such as 10, 20, or even 30 presentations of all of Shakespeare works, but the gain would likely be rather small.
So our first aim was actually music generation neural network, and so that it reads in MIDI files and generate music pieces on its own with similar music style from the input. But soon we realized it's hard to model music, and we don't have time to actually learn music theory stuff to have a perfect model that embeds dependencies between chords and notes and stuff. And here is one of those embeddings, and we are not satisfied with embeddings as complicated as this, but we couldn't think of better ones though. So to sum up, we faced a lot of problems and obstacles. We all went from scratch on this project without any prior knowledge or experience with neural networks, Python, or TensorFlow. We spent tens of hours on tutorials and documentation and videos to setting up the running environments and to learn how to run Python and specifically TensorFlow codes. And we spent more hours to read tons of papers to get an idea of what's going on behind the codes, like how does a models work and why does it fail in some cases, and how to solve those problems, just like the vanishing gradient problem. It was hard to learn the math and theoretical stuff, but we went through it and actually pretty much enjoyed it. And for future work, one of the papers talk about attention layers to add to RNN models that will select features to be learned to make the learning progress even more effective for long-term dependencies. We will definitely play around with that and our Shakespeare playwriting code if you have more time, so that it can learn long time. It may be able to write even longer stories with admirable logic. And the other thing is, we plan to do music generation at first, so maybe in the long run, we would like to learn and experiment with music and music series and RNNs in the future. Finally, the most viable option for us right now would be manipulating our code in more ways, such as using different activation functions, combine different neural network models like CNNs, and even tweak the recurrent cells, like adding different layers of recurrent cells, or adding leak points to the cell states and the hidden states, and to see how we can optimize the network using all these different open source code mechanisms and techniques. So that's it. Here are all the references we've been using. It's really a ton of work.